Good morning. So this morning what I want to talk about is computing a derived graph using Fluo. And the purpose of this talk is to try to give a use case to show how one might use Fluo and to help contextualize things. Because when you start looking into the big data space and you look at all the things that are there, it can be hard to know why you would use this or that. Because what happens is a lot of these projects and products, they make different trade-offs that have to be made when you're working at scale. So they offer different capabilities. So I'm going to try to show what capability Fluo offers and the niche it fills. So Fluo is based on Percolator, which is a paper released by Google. And this is the use case that's described in the Percolator paper. So Google developed this because they have their own copy of the web sitting on their clusters, petabytes of data, and then every day they're crawling the web and bringing in updates to that. Now what they used to do is they would run, like in the paper I think they said a series of like 100 MapReduce jobs to take their copy of the web, petabytes of data plus the terabytes of new data, and produce an index of the entire web. And I think in the paper they said this would take like 3 days. So what that meant was when they crawled a new document, however long that took, as soon as it got crawled, it wouldn't show up and be searchable, the changes in content for the document, for about 3 days. So they developed Percolator to lower that latency to minutes. So they went from days to minutes for that latency for updates. And we'll go through this in the paper and show how they were able to do this. And I think they built a product on top of Percolator. I think it was called Caffeine. So they had Percolator offers one capability, and then it offers a capability similar to MapReduce. It's a very generic capability, and they built something more specific on top of that. So what Percolator and Fluo offer are two primary things. Cross-node transactions. So the ability to make changes to data that exist on multiple nodes in a cluster, and either all of those changes go through or none of them go through. And the second thing that it offers is something called observers. And observers are user-provided code that execute when a certain column is changed in Accumulo. So, and what happens is one transaction can set notifications that will trigger follow-on transactions to execute. So your processing it becomes like a chain of these transactions, manipulating the data. And I don't know if I mentioned this, Fluo is an implementation of Percolator that's currently an Apache top-level project, this Apache Fluo. And it builds on top of Accumulo. So this shows the components of Fluo. So as a user, you have client processes that use the Fluo API and execute transactions. These client apps would normally be loading data into Fluo. And then within the cluster, you have an Oracle process that's run per Fluo application. And as a user of Fluo, you'll never interact with this directly, but it's just a component that's out there running on the cluster, and it's providing logical timestamps. The user code that you provide, observers, are run by Fluo workers. So Fluo workers, they run on the cluster. You could run one on each node. They're continually scanning the table, looking for notifications that were set by transactions and looking for work to do. And then once they find a notification, they'll spin off user code to execute a transaction. Each Fluo application has a table associated with it in Accumulo. And Fluo stores its metadata in Zookeeper. So like the Oracle, with its logical timestamps, it stores information in Zookeeper, so the next time it starts, it can keep track of the next logical timestamp. And right now, with the current release of Fluo, there's two ways you can run it. You can go to each process and start a Fluo worker and start an Oracle somewhere. Or you can use Yarn to automatically spin up Fluo workers and the Oracle across the cluster. In the next release of Fluo 1.2, we're working on the ability to support Kubernetes and Mesos for running Fluo. And really what that comes down to is making Fluo work well in Docker. And it seems like that would be simple, but there's actually a lot of little gotchas once you actually try to go do it. And we're actually working through those, and we'll have a version of Fluo that runs in Docker. Then you can use that to run in Mesos and Kubernetes. That runs well in Docker, I should say. So the use case I'm going to talk about today is a derived graph. It could be any graph. For the sake of an example, I've used social network data. So in the example, we're going to have multiple social networks and their graphs. Assume the links mean follows in this case. So we have like Twitter user T1 follows Twitter user T3. That's what that's showing there. And then for GitHub, we have GitHub user G1 follows GitHub user G4. Oh, I got that backwards. G4 follows G1. I couldn't see the arrow properly over there at this angle. Now let's assume we have something like a machine learning type system that's going through possibly something like web pages, blog posts, and finding relationships between these users in different social networks. And it's figuring out that they're actually represent the same entity. So we're running these analytics. Now this is outside of Fluo, but we're running these analytics and it's generating these relationships saying, oh, the Twitter user T1 and the GitHub user G1 are actually aliased, actually seem to be the same entity, this A1 user that we've created. So when we take all the aliases, we can create a derived graph where we pull the links from all the three graphs above and generate this virtual graph that has all the follows relationships from all the different raw graphs. So for instance, like we have the user T1 follows T3, and then T1 is alias to A1 and A3, so we get that follows relationship between A1 and A3 from Twitter. And then we have a follows relationship from A3 to A1 coming from Facebook, coming from F3 and F1. Now, ideally, what we want to happen is when we add an edge to one of the raw graphs, so like a new edge comes in from G3 to G4. And I don't know if you guys can see it, but it's in the GitHub graph, it's in orange. We would like, when that edge comes in the raw data, that it shows up in the derived graph. So now we have the edge between A3 and A4 from a new edge in the derived graph, in the raw graph. Now also assume we have another analytics system that's going through. It could be looking at web pages again, and it's coming up with attributes about these nodes. For instance, so for Twitter user T4, our analytics determine that seems to be time zone GMT. And then for GitHub user G4, we have a location of 4 privet drive. And anyone's familiar with Harry Potter, they'll know where that comes from. What we want to happen is we want those attributes in the raw graph to come down to the derived graph. So we had T4 and G4 actually alias to the same user, A4, so those attributes show up there. So putting this use case all together, we have basically 3 inputs. We have the raw graph data from multiple social networks. We have alias analytics, attribute analytics, and they're all continually feeding Fluo. And Fluo is continually joining these large data sets and recomputing the derived graph. And as it changes, it's emitting updates to external systems. That could be a query system that stores the graph, and you actually want to do queries on the graph. Or it could be a follow-on analytics system. Now this is just to give some context. I'm sure everyone knows this, but it's a good reminder. It's like, why do we use things like MapReduce? Why do we use things like Fluo? This is the trade-offs I was talking about earlier. It's because the data doesn't fit. We have multiple large data sets, and none of them fit on a single machine. So like the Twitter data spans multiple machines. The GitHub data spans multiple machines. The alias data spans multiple machines. The derived graph spans multiple machines. So when you have this situation, you get into these trade-offs. Do Do you want this or that? Because you can't do everything in milliseconds as customers may want when your data doesn't all fit on one machine. So what I'm going to walk through before I walk through how we would do this with Fluo is how you would use MapReduce to create the derived graph. So using MapReduce, you'll do 3 to 4 MapReduce jobs to generate the derived graph. And then you've only generated the derived graph. If you want to do follow-on analysis or create or indexing of the derived graph, you have to do additional MapReduce jobs. So it's just 3 to 4 MapReduce jobs just to materialize the derived graph. So this is the first job, and I'm just showing the input and output of the job. So the input, we have our alias data, and we have our edges. And what we want to do is for all the edges, take the first half of every edge and join it with the alias data. So after this MapReduce job completes, my edges are half done. Like their first half has the alias IDs that have been replaced in the raw IDs. And then just for the sake of provenance, I'm keeping the original edges. And then you do a second MapReduce job that goes over the second half of all the edges and joins them with the alias data. So like the node, this edge A1 to A3, I replace T3 with A3. And you see I get the generated graph. So after this, I've materialized the edges for the derived graph. So in 2 MapReduce jobs. Now, if you want the edges to be unique, this depends on your processing, what you're going to do afterwards. You may have to do a third MapReduce job to unique the edges. Because like I ended up with this edge A1, A3. It came from Twitter data and Facebook data, and I ended up with a duplicate edge there. And that edge will be, after MapReduce completes, will probably be on different machines. So if I want to unique the edges, I've got to run another MapReduce job. And the final MapReduce job is to combine the attribute data and the alias data to join those two things. And then to get the attributes associated with the alias nodes. And then once you've done all that, you've materialized the attributes for the alias attribute combination. You've materialized the edges for the raw graph. And now you can actually do further MapReduce jobs to actually do something with the derived graph, because all you've done so far is materialize it. So using Fluo, what you're going to do is your input's going to be the raw edges, raw node attributes, and the alias data. And I've created a little prototype, and I'm going to show that towards the end, just screenshots of it. And what's going to happen is Fluo is going to take these inputs, it's going to kick off a series of transactions, it's going to materialize the derived graph. And then as the derived graph changes, in the prototype it just emits changes to an external query system, which is just another Accumulo table. And it removes and deletes things from that other Accumulo table. So the first step I want to walk through is how you would add a new edge in Fluo. So when we start off, we have an Accumulo table that has some data in it. This is the Accumulo Fluo table. And it has some alias data, and that's it to start off with. And what we want to do is we want to have a transaction to add this new edge T1 to T5. So the first thing that transaction is going to do is it's going to read the alias for T1 and read the alias for T5 into memory. And then the next step is it's going to write out 4 things. Now conceptually what I'm doing here is for each node in the graph, I want to keep a list of its edges. So that means for like this T1, T5 edge, I'm going to add it to the T5 node, I'm going to add it to the T1 node. Now also I had read in the aliases for T1 and T5, and I'm going to update the A1 node with an edge to A5, and I'm going to update the A5 node with an edge to A1. Now I'm also keeping with the T1 and the T1 T5 edges, I'm keeping what aliases I used. So when you're writing Fluo applications, one thing you have to start kind of thinking in a bit of a stateful type way. Start thinking of state machines and things like that, like what's the state of it now? And then the transactions will help you mutate that state atomically. But you still have to get in a little bit different mindset than writing MapReduce applications. And with the aliases, I'm also setting the state of the edge to new. And I'll talk about that a little bit more in a second. But this thing is, so this transaction is changing 4 things, and those 4 things could be actually stored on 4 different nodes, 4 different tablet servers in the cluster. And what's nice about Fluo is you have this, it gives you this nice sane layer where those tablet servers could be dying while you're doing this, the thing executing this transaction could be dying, all kinds of insanity could be happening. But either all 4 of those changes will go through or none of them will go through. And when you get used to that, it's kind of nice because there's so much insanity when you start dealing with hundreds of nodes. Nodes are going down, nodes are misconfigured, all kinds of crazy stuff going on. Now, what the transaction does is it sets 2 notifications. It sets a notification on A1 and A5. And what that's going to do is trigger subsequent work. So this transaction is not going to do anything about recomputing the state of the derived nodes. It's just setting 2 notifications that says, okay, let's trigger some follow-on work to update those, or to reprocess those guys now that they've changed. And then after it commits, all the changes go through and the 2 notifications are left behind. So the next thing I'm going to go through is what happens when something processes a notification. So we have a transaction that started executing because a notification was set on A1. And what it's going to do is it's going to read the current state of A1 and try to figure out what's changed and then compute the new state of it. So it reads that, oh, A1 has this new edge to A5. And it's going to process, it's going to mark that edge, oh, that edge is no longer new, so it's going to make that change. And it's also going to put something on an export queue. And export queues are something I actually talked about last year when I talked at the Accumulo Summit. But what an export queue does is, or the reason it exists is when you're in the middle of a transaction, like if you're computing the new state of the edge A1, you don't want to, in the middle of that transaction, start exporting things to an external system. Because if your transaction fails and the next time you come run it, you may compute a different state. And maybe depending on the last state, you were deleting things and adding things to the index table, and you could end up making the index table inconsistent. So a good strategy, and there was like 1 sentence for this in the percolator paper, is to have something like an export queue, where you put what you want to export on this export queue, and the export queue exists within Fluo. So it's part of the transactional update. So as you're computing the new state of the node and throwing this thing on the export queue, it either all goes through or none of it goes through. And what you're putting on the export queue are basically idempotent operations. They're operations that it's okay when you're trying to export to keep trying them over and over until they succeed. And what would happen is if I didn't have this time to actually show this with graphics, but if you had multiple updates for A1, you may end up queuing a lot of updates for A1 on the export queue. And you would work your way through them, doing whatever they wanted to add and remove to your index table. But when we computed the new state of the node, we put on the export queue that A1 has 0 followers and 1 following. And then we do the same thing for A5. And we throw something on the export queue for it. But A5 actually has different followers and following. And I'll talk about something a bit later on why those are duplicated. I have an example that will show that. Because they're not quite duplicated. What's happening is A1 is queuing updates for all of its neighbors, and A5 is queuing updates for all of its neighbors, each doing that with information about their self. So the next set of operations I want to talk about is how you would do the alias change in Fluo. So to set up this scenario, so there's a transaction executing as part of a notification. And the reason it's executing is because the alias for T5 was changed. So let's assume that T5's alias used to be A5, and something changed its alias to A7 and set a notification. And that caused this transaction to kick off. So the transaction is going to read the current state of T5. It's going to see, oh, its alias is A7 now, and it has this edge, T1 to T5, that seems to be using the alias A5 right now, the old alias. So it's like, I need to fix that. So what it's going to do is it's going to update T1 and T5, because every node keeps track of a list of all of its edges. But it's also going to update the nodes A1, A5, and A7. So it's got to delete an edge for A1, A5. It's got to add an edge for A1, A7, delete the A5, A1, and then add the A7, A1. So it's making 6 updates. And again, these 6 updates could be to 6 different nodes in the cluster, and they'll all go through, or none of them will go through. And then it's also going to set notifications on all 3 of the derived nodes, saying that all of those changed. And that will trigger 3 follow-on transactions to recompute the state of those nodes, and then queue exports to update your external query system or analytics system that say, hey, the derived graph changed, and here's what I recomputed about the derived nodes. So after the transaction commits, the notifications are left behind. Now, another thing you have to think about when you're working with Fluo is concurrency. It's something you don't have to think about so much when you're writing like MapReduce or Spark jobs. Fluo gives you the tools to handle concurrency, but you still have to be aware of it when you're writing Fluo applications. So this is looking at the scenario where you have 2 nodes, like 2 Twitter nodes, T1 and T5, and both of their aliases were changed. And that's going to cause 2 transactions to try to process those. So I have transaction 1 and transaction 2. They're both trying to deal with this situation. And what happens is they both try to change the same data at the same time. Now, the way Fluo works is it uses something that I think is generally called optimistic locking. It's like you don't lock things up front. You just read all your data, compute your changes, and then you write them. And as long as nothing changed since the time your transaction started, everything will go through fine. If things changed since your transaction started, then what will happen is that'll be a collision. It'll cause the transaction to fail. And in the observer case where Fluo has a worker running notifications, it will just automatically rerun the transaction with exponential backoff. So in this case, one of these transactions will fail likely, and one of them will succeed. And then the one that failed will automatically be rerun. And then you'll end up with the correct state for the 2 nodes. So I didn't think I had time, so I didn't go through the transactions for adding an attribute to the graph. But if anyone has questions about that, I could go over it later. So the little prototype that I wrote, I don't have it up on GitHub yet. I'll have it on GitHub probably sometime within the next few days. But I have screenshots of it here. And it's pretty simple. What it allows you to do is add, remove edges, aliases, and attributes. And then it exports changes to the derived graph to an external Accumulo table that you can query. And it's really easy to run just to get started with. You just need to clone it, and then you run one script to start mini Accumulo and mini Fluo, and that starts up the application. And then you run another little script which gives you a shell where you can do these operations, add, remove edges, aliases, and attributes. So this is my screenshot, and don't worry, I have some pictures to go along with this in a second. But what it's doing is it's creating a simple graph with the follow operation. So what that's saying is, oh, in the Twitter graph, so follow TW, in the Twitter graph, create an edge between Bob99 and Alice95. And then it's saying, alias the Twitter graph user Bob99 to just Bob. And then later, we come down here and do lookup Bob, and that goes to the external query table and looks up the information we currently have about Bob. And what's interesting is we also have pre-computed, when we look up Bob, in one lookup, we get the pre-computed information about its neighbor, how many followers and following it has. So here are my pictures to help show what's going on. Maybe this makes it a little more clear. So the picture is showing the data in Fluo and the data in the query table up to this point. So I've executed all these follow operations, and that created the graph. And then I executed these 3 alias operations, and that kind of grouped 3 Bob users from 3 different social networks into 1 virtual user. So when I query Bob, I get these links going out. Now also notice for the Alice user, I have some attributes. So for the Twitter Alice95 user, I have a location attribute, location equal TX. And then for the GitHub Alice++ user, I have an attribute TZ equals CST. And then notice when I query Bob, right now I'm only seeing, because there are no aliases for Alice right now, I only have the link from Bob to Twitter Alice. And so I only have the location equal Texas information. Now, once I add the aliases for Alice, that does a few things. It causes the link between Bob and Twitter Alice to be deleted in the query table. And it causes a new edge to be added between Bob and the alias Alice. And notice now that even though there's no direct link in the graph between one of the Bob users and the GitHub Alice user with the TZ attribute, that I have that pre-computed for the Alice node because it got pulled together in the virtual derived node. And this concept, it's simple, but I have a hard time explaining it. It's a concept that I call invert on export. And I was trying to talk about this a little bit earlier, like why I had 2 things on the export queue. But basically what happens is when the virtual Alice node changes, it computes its new state, and it throws that on the export queue. And when the export operation actually happens, it updates all of Alice's neighbors in the query table with the information about Alice. So when Alice changes, it doesn't actually update Alice in the external query table. When Alice changes, it only updates Alice's neighbors. So when Alice changed, it updated Bob in the query table. So it's like we're actually doing one last join outside of Fluo by just inserting into the Accumulo table. So and then we add the aliases for Joe to bring all the Joe users under 1 virtual user. And that causes more links to be deleted in the derived table. And then we add these links to, from Bob, directly from Bob to Joe in the query table. And we get this following equal to. So that's actually computed from the alias information because you can't see that without the alias information because one of the followers, there's no direct link between Facebook Joe and Bob. So we're actually getting information about that follower by joining the alias information. And then it's all pre-computed for the Joe user and put in the Bob node so you can get it with one query. Now it's interesting to think about, like, okay, what if I didn't use Fluo for this? Because in this use case, the only reason you would be using Fluo is to speed up your queries. So you're doing, it's a common technique with databases. You do it for a long time. You build indexes, you pre-compute things to speed up queries. So without pre-computing this, to actually get this information to the user, you would have to start off and query the Bob alias. And then you would go to all the nodes that were mentioned for that alias. And then you would query all of them. So you would query, you would start off with Bob, you would query Twitter Bob 99, GitHub plus Bob, and Google plus Bob, and GitHub Bob 799. So you query those three. Then you get all of their neighbors. And then you got to go look up their aliases. And if you want to get information about them, you actually have to query them. And then if you want to deconflict that, you have to query their neighbors too. So you have to do like this 3, 4, I get lost. I should have had a picture with that, I'm sorry I didn't. But you have to do a lot of multi-step queries and then join all the information on the client side. So it's just a speed trade-off. So you could definitely do that at query time, but it would be a lot slower. So if anyone's interested in getting started with Fluo, on the website there's something called the Fluo Tour. And this is based on, it's based on two things. So I had taught some Fluo classes in the past, and I took that information and I put it on the website. But the structure of the information was inspired by the Golang tour. And the Golang tour is you just go through all these exercises to learn the Go programming language. And each exercise is kind of self-contained and pretty independent. So that the Fluo Tour kind of tries to follow that, where it introduces a concept, and then with each concept, you have an exercise that goes along with it, and then you can just focus on that concept. And you put all these concepts together, that's a whole nother aspect. Like actually, it's like programming. It's like, well, I've learned if and for and while. And my niece just started computer science, and she's trying to put all this together. So you learn all the concepts, that's the first step. And then the next step is you learn techniques for putting those primitives together. But the Fluo Tour mainly just helps you learn the primitives. And then learning how to put them together is a whole nother thing that needs to be written up at some point. And this is the website for Fluo, and that concludes my talk. If anyone has any questions. So I've published studies, we have this application called WebIndex, and it's not doing this exactly. It's pre-computing, it's inverting links and computing counts and information about them. And we run that with something called Common Crawl data, which is, I don't know who does this. It's a nonprofit, but I don't know who actually sponsors it, funds it. But they just crawl the web, and they have petabytes of data sitting in Amazon S3. So we have plenty of real data, and we could just start sucking that in and throwing it into Fluo. So the tests we've ran would be like 20, I think on a 20-node Amazon cluster with 20 small nodes, running for 3 days, I can get a sustained rate of like 8,000, processing like 8,000 links per second. So that's just links, and what Fluo has to do is multiple operations per link. So that results in a lot of transactions per link. And I'm not sure if I have those numbers right. I would have to go back and look. But then you multiply 8,000 times 86,000, whatever, how many seconds are in a day, and you get about how many links that can process per day. And that's the main thing we have for numbers. And I don't know, I think that's 1 billion something per day on that 20-node cluster. So, yeah, and it's a space-time trade-off. So one thing interesting about this architecture is when you run like a series of MapReduce jobs, you usually have intermediate data between the two. You usually throw that out, right? Like when you're done, you just throw it out. But with Fluo, you're keeping all this intermediate data around for your computation conceptually. So you're going to use more space in order to cut down on latency. So. Yeah, I think there's, so what I tended to do with this example is I tried to make the operations, most of the operations more node-centric to try to cut down on that chance. Because if there's more edge-centric, then they do you tend to increase, because there's okay, wait, let me back this up. I had to think about how I did that. So I tried to make the edge operations modify the nodes such that the edge operations don't collide. So what I did was when you add a new edge, it triggers a follow-on transaction to say, oh, the Twitter edge changed, and here's the changes, and it'll process that node at once. So that if I had like 5 edges for the same Twitter node, they wouldn't collide. And then if there's an alias change, that's also a node operation. So what happens if you have these node operations, these edge operations coming in, and the alias operation, they all trigger an observer on the Twitter node. And then I did that to try to cut down on the probability of transaction or collisions. So, and I've actually, based on doing this, so to do that I had to do 2 transactions. So I would make the edge operation trigger a follow-on node operation. And what it would do is say, oh, did the alias change? I'm toying around with adding read locks so that you can actually read data and the transaction will collide if it changed while you were executing. So it's not something that Percolator currently has. And Google said they didn't do it on everything because read locks for every operation didn't make sense. But I think targeted read locks where you can actually say, I want to do this with a read lock, I think that makes sense. So I'm going to be reading a whole bunch of things, but I can read just this one thing, like I'm going to read the attribute with a read lock. And then if it changes, then I'll retry. So. No, it's me, the developer, thinking about concurrency and collisions and structuring this in such a way that, so I structured it in such a way that every edge operation doesn't get a write lock on the node. Because I think that's what you were getting at. It's a very good point. It's something I didn't have enough time to explain, but if I have a node from T1 to T5, and I got a write lock on T1 and T5 when I added that edge, and then I also had attribute operations getting a write lock, then the probability of collision goes way up. So what I did for the edge operations is I added the edge to T1 and T5, and then I set a notification on both of those to say you have a new edge and process it. So because it converts that edge operation into a node operation to cut down on the possibility of collisions. There's no intrinsic limit, and I've only done things that probably have currently a depth of 3 or 4. But I think like with this derived graph, I think like I was talking about with the MapReduce job, you materialize the derived graph and then you do interesting things on it after you've materialized it. I think you could do that same type of thing in Fluo where you've materialized that derived graph and then you want to do follow-on transactions to do further computations on the derived graph itself. Like you could join it with more data that you're bringing in. No, because that gets back to where I was converting the edge operations to node operations. So it's kind of like for each node, you queue up the changing edges, then you set a notification on that node. Here's the new things. And it recomputes its new state. So if it got an edge going out and an edge coming in, it would just recompute its state. Does that make sense? Or was it? Okay. All right. Thanks everyone for attending.